Good morning, all of you. We are moving on to the last part of ionic equilibria, the topic that is salt hydrolysis. Salt hydrolysis. See here, salt hydrolysis means that is when we are mixing an acid or a base, acid and a base in water. What happens is that the solution will be becoming neutral, isn't it? If we are mixing an acid and a base in water, it will be becoming a neutral solution. So when a strong acid, if we are mixing a strong acid with a weak base, if we are mixing a strong acid with a weak base, what happens is that the strong acid means it will be completely ionized in solution. At the same time, weak base, it will be partially ionized. Only partial ionization takes place in the case of weak base, but in the case of strong acid, it will be completely ionized. So what happens is that the resulting solution, the so formed solution, what about the nature of the solution? The resulting solution, it will be an acidic solution because the ions which are, that means the ionized, completely ionized acid, it will be remaining, or the acidic ions will be remaining in the solution. The weak basic ions will be completely neutralized. So here, when we are mixing a strong acid with a weak base, what happens? The resulting solution will be acidic. Then if we are adding, or if we are taking a weak acid and a strong base, weak acid and a strong base, then we can say that the resulting solution will be a basic one or an alkaline one. The resulting solution will be an alkaline one because the strong base, it will be completely ionized, and the resulting solution will be having OH minus ions, the basic ions in excess. So therefore the resulting solution will be alkaline in nature. And again, when both acid and base are weak, what happens is that both, if we are taking a weak acid and a weak base, weak acid and weak base, then the resulting solution, we cannot predict the solution, the strength, we cannot predict the nature of the solution. The nature of the solution, it depends on the strength of the solutions. That means whether the acidic, it depends on the acidic strength or the basic strength. If the acid strength is greater, then the resulting solution will be somewhat acidic in nature, and if the basic strength is greater, then we can say that the resulting solution will be basic in nature. So if we are mixing a weak acid and weak base, we can say that the resulting solution, it depends upon the strength of the acids or bases we are mixing. Okay, so this is the third case. So first one we have discussed is the strong acid weak base, then second one weak acid strong base, then third one weak acid weak base, and the fourth one, that is a strong acid strong base. What about this case? A strong acid and a strong base. Here both of them will be completely ionized, isn't it? So what happens? The resulting solution will be a neutral solution. Okay, so these are the four cases. So here we are discussing about the salt hydrolysis, and here the acidity or alkalinity, that is some solutions are acidic in nature while some solutions are basic in nature. So the acidity or alkalinity of the solutions, it means it is the tendency of the solutions or tendency of the salt solution, the resulting salt solution to react with water, isn't it? Here both acid and a base reacts together to form a salt, and that salt reacts with water. So that decides the resulting solution. Okay, so this process, it is just opposite to that of neutralization, and this process, it is called as the salt hydrolysis. That means here the acid or base, that is here the acid or base, it will be reacting together to form a salt, and again the salt, it will be reacting with water. That is, in solutions we are doing all this. So the so formed salt will be reacting with water to form what happens to form a solution of acidic or basic nature. So this phenomenon of interaction of anions or cations, the phenomenon of interactions of anions or cations with H plus or OH minus ions. H plus or OH minus ions means they will be coming from water, isn't it? So this anion or cation, they will be coming from the acidic as well as the basic solution, and the interaction of the anions or cations with H plus or OH minus ions furnished by water to yield an alkaline solution or an acidic solution. To yield an alkaline or an acidic solution, that phenomenon, it is called as the salt hydrolysis. So this phenomenon, it is called as the salt hydrolysis. So salt hydrolysis or hydrolysis of salt. So the definition is that the phenomenon of interaction of anions or cations. The phenomenon of interaction of anions or cations phenomenon of interaction of anions or cations with H plus or OH minus, with H plus or OH minus to form an acidic or alkaline solution. It is called as the salt hydrolysis. So the resulting solution, it depends on this interaction. Okay, the strength of the solution, it depends on the interaction of the ions of the salt. So based on this, we can the salt hydrolysis, we can classify it into 4 categories. That means the first we have discussed it, that is the first case, that is the strong acid weak base, then weak acid strong base, then weak acid weak base, and the fourth one strong acid strong base. Okay, so these are the 4 distinct groups of salt hydrolysis. The 4 groups of salt hydrolysis. I will be writing in short form. 4 groups of salt hydrolysis. The first one, that is the strong acid and strong base. Second one, strong acid, weak base. Then third one, weak acid, strong base. And the fourth one, weak acid and weak base. So these are the 4 categories of salt. Okay, so let us see one by one, and we have to deduce some formulas also for this one, and there are problems related with this salt hydrolysis. The problems is very simple. You can just substitute in the formula and you can find out the values, corresponding values. Okay, so the first case, that is the salt of strong acid, salt of strong acids and strong bases. Salts of strong acids and strong bases. See, consider the salt Ba. It is a salt of a strong acid and a strong base. So Ba plus H2O. It will be ionizing as this equation I had already taught you. So giving BOH plus HA. And again this Ba, it will be completely ionized. Sorry, first case we can go through strong acids and weak bases. Okay, strong acids and weak bases. Salt of strong acids and weak bases. So here this is a salt of a strong acid and a weak base, Ba plus H2O giving BOH plus HA. So what about the resulting solution? The resulting solution will be an acidic solution, since we are taking a strong acid, isn't it? So the resulting solution will be an acidic solution. So here what happens, this Ba is completely ionized, and also the acid being strong, it will be completely dissociated. So this part will be completely dissociated. This is the acid part, this is the basic part. Okay, so let us write down. So this B plus plus A minus plus H2O giving, this is the basic part, it will not be completely ionized, plus HA, it is the acidic part, so H plus plus A minus. Okay, so here this A minus got cancelled, so the resulting equation will be B plus plus H2O giving BOH plus H plus. Okay, so therefore we can write the equilibrium constant. The equilibrium constant K is equal to, how will you write? Concentration of BOH into concentration of H plus divided by concentration of B plus into concentration of H2O. This also we had already seen, isn't it? This type of derivation we had already seen. Then again, this the concentration of water, it is a constant, so we can cross multiply it with K. So therefore we can write it as K into concentration of H2O, that is equal to concentration of BOH into concentration of H plus divided by concentration of B plus. Okay. Then again, two constants, if two constants are multiplied, we will be getting another constant. So we can write it as KH. Okay. KH is equal to concentration of BOH into concentration of H plus divided by concentration of B plus. Okay. Let us put this one as equation number 1. So here KH, it is called as the hydrolysis constant. So here KH is called as the hydrolysis constant. KH is called as the hydrolysis constant or the hydrolytic constant. Okay. So this is a simple derivation using this particular equation. Then the next is the relation between KH, KB and KW. Relation between KH, KB and KW. So here we are taking a strong acid and a weak base, isn't it? So the weak base, here the weak base is BOH. This is the weak base, and this weak base, it will be ionizing as, only partial ionization takes place, and it will be ionizing as B plus plus OH minus. Therefore, the ionization constant, that is Kb, is equal to concentration of B plus into concentration of OH minus divided by concentration of BOH. Okay. So this is the ionization constant Kb. Put it as equation number 2. Then again, so here we are finding out the relation between KH, KB and KW, isn't it? So already we have got this KH. Now we have to find out KB and KW. So KB is equal to this much. Then we have to find out KW. Okay. So for finding out KW, what is KW? It is the ionic product of water. KW is called as the ionic product of water. Therefore, water will be ionizing as H2O, giving H plus plus OH minus. Okay, so therefore KW, that is equal to concentration of H plus into concentration of OH minus. Okay, so this is equation number 3. So dividing KW by KB, that is equation 3 divided by equation 2. Equation 3 divided by equation 2. So while writing, you have to write the steps also in the LHS. So equation 3 divided by equation 2, that means KW by KB. KW by KB, that is equal to, what is KW? That is H plus into OH minus. H plus into OH minus divided by KB is B plus into OH minus divided by BOH. That is B plus into OH minus divided by BOH. So it will be going to the numerator into BOH. Okay, so what all terms got cancelled? This OH minus will be cancelling. So the remaining will be H plus into BOH divided by B plus. That is equal to H plus into BOH divided by B plus. Okay, so what about KH? What is the value of KH? So put it as equation number 4. So we have seen the value of KH. KH is equal to BOH into H plus divided by B plus, isn't it? Both are the same, isn't it? BOH into H plus divided by B plus. Therefore, while we are dividing KW by KB, we will be getting KH. So therefore, KH is equal to Kw by Kb. Okay, that is from equation 4 and from equation 1, isn't it? From equation 4 and equation 1. Okay, so therefore Kh is equal to Kw by Kb. So this is the relation connecting the hydrolysis constant, then ionic product of water and the ionization constant of a weak base. Then the next is relation between. So all these derivations are important. This might be asked. Relation between hydrolysis constant, relation between hydrolysis constant and degree of hydrolysis. Relation between hydrolysis constant and degree of hydrolysis. See here, degree of hydrolysis, it is represented by the letter alpha. We had already seen, I think, isn't it? Degree of hydrolysis, it is denoted by alpha, and also, so not alpha, it is denoted by H, sorry, denoted by H. Degree of hydrolysis denoted by H. So here degree of hydrolysis means it is the fraction of the total amount of salt undergoing hydrolysis. Fraction of the total amount of salt undergoing hydrolysis. It is the fraction of the total amount of salt undergoing hydrolysis, that is called as the degree of hydrolysis. So here we are considering the salt Ba. Okay, so Ba in water, it will be ionizing as BOH plus HA, and here we are considering a weak base and a strong acid. Therefore the strong acid will be completely ionizing, isn't it? So Ba plus H2O ionizes to give BOH plus H plus A minus. Okay, so this we can write it as B plus A minus, isn't it, as in the previous case. So A minus got cancelled, so B plus H2O giving BOH plus H plus. Okay, so if the initial concentration of B, if it is 1, then here it will be 0, 0, and after a time t, what happens? The alpha will be dissociating. So the concentration of B at equilibrium, what happens to the concentration of B at equilibrium? Sorry, B plus at equilibrium, it will be 1 minus alpha, isn't it? Alpha will be dissociating. So this will be 1 minus alpha, and what happens to BOH? It will be alpha and alpha, isn't it? Alpha got dissociated. So at equilibrium, so here we are multiplying it with the concentration, then it becomes C alpha. Okay, so the concentration of B plus at equilibrium will be equal to C into 1 minus alpha, and also in the case of BOH it will be C alpha, and H plus it will be C alpha. Okay, therefore, as you know, what about KH? From this equation we can write KH is equal to concentration of BOH into concentration of H plus divided by concentration of B plus, isn't it? Already we had written, isn't it? So KH is equal to concentration of BOH into concentration of H plus divided by concentration of B plus. Then you have to substitute for all these values. So what about the concentration of BOH? BOH is C alpha, H plus is C alpha. So C alpha into C alpha divided by C into 1 minus alpha, isn't it? For B plus it is 1 minus alpha. Concentration of B plus is 1 minus alpha, isn't it? C into 1 minus alpha. So here the C got cancelled, so it will be equal to C alpha square divided by 1 minus alpha. Again 1 minus alpha, it is approximately equal to 1 minus alpha is approximately equal to 1. Therefore KH is equal to, how will you write? KH is equal to C alpha square, isn't it? Therefore, what is alpha? Alpha is equal to square root of Kh divided by C. Alpha is equal to square root of Kh divided by C. Already we had got what is Kh? Kh is equal to Kw by Kb, isn't it? So we can substitute for Kh. Therefore, alpha is equal to square root of Kh is equal to Kw by Kb, Kw by Kb into C. So therefore, alpha is equal to square root of Kw by Kb into C. So this is the alpha or hydrolysis constant. So this is the relation connecting hydrolysis constant and degree of hydrolysis. Okay. Then the next one, that is the H plus ion concentration and pH. H plus ion concentration and pH. So here from this equation, what is H plus ion concentration? H plus ion concentration, that is equal to C alpha, isn't it? From this equation, H plus ion concentration is equal to C alpha. That is equal to C into square root of Kw by Kb into C, isn't it? So that is equal to, again we can cancel this C, isn't it? Both if this is root C into root C, then it will got one root C will got cancelled. So therefore we will be getting square root of C into Kw divided by Kb, isn't it? Concentration of H plus. Then again, what about pH? pH we can write as minus log H plus, isn't it? So here for converting to that form, we have to write the we have to take the logarithm. So log H plus, so this is H plus, isn't it? So taking logarithms on both sides, taking logarithms on both sides, log H plus is equal to, log H plus is equal to, this square root means we can write it as half, isn't it? Half into log C, half into log C plus log Kw. We are taking logarithms for all the terms. Then divided by Kb means minus log Kb. Minus log Kb, isn't it? So again, what is the next step? For pH, the formula is minus log H plus. So you have to convert the sign. That is minus log H plus. Okay, minus log H plus, that is equal to half into, here it becomes minus log C. Then again this becomes minus log Kw. Again this becomes plus log Kb. Plus log Kb. So this is in the form of pH, isn't it? Minus log H plus, that is equal to pH. pH is equal to half into minus log C. That means it can be written as such, minus log C, then minus log Kw. That means plus pKw. That is pKw is equal to minus log Kw. So we can write this term as a whole as pKw, isn't it? Then plus log Kb. Plus log Kb means pKb means it will be minus log Kb. So this becomes minus pKb. Okay, so we can write it in the correct form. So pH is equal to half into pKw minus pKb minus log C. Half into pKw minus pKb minus log C. Okay, so this is the form. So this is the pH of the solution having a strong acid and a weak base. Okay, so the solution will be acidic. Then we have to write some of the examples for the strong acids and weak bases. Examples for strong acids and weak bases. Example, ammonium chloride. Ammonium chloride plus H2O, that is ammonium chloride is undergoing hydrolysis. So it will be forming ammonium hydroxide, isn't it? Ammonium hydroxide plus HCl. Okay, so here this ammonium chloride, it will be undergoing complete dissociation, and the strong acid HCl will also undergoes complete dissociation. So ammonium chloride will be dissociating as NH4 plus Cl minus plus H2O, giving, this is a weak base, so it will not be completely dissociating. So we can write it as such, plus HCl, it will be ionizing as H plus plus Cl minus. Okay, that is the Cl minus will be cancelled. So ammonium NH4 plus plus H2O, giving NH4OH plus H plus. Okay, see here, what about the resulting solution? The resulting solution will be becoming acidic because it will be having H plus ions, isn't it? So the resulting solution is acidic. The resulting solution is acidic due to the presence of H plus ions. Due to the presence of H plus ions. Okay, so this is how we are finding out the strength of the solution or the nature of the solution. Then another example, that is ferric chloride. Second example, ferric chloride, FeCl3. So FeCl3, it will be ionizing, or it will be in solution, or it will be reacting with water to form ferric hydroxide, FeOH thrice, isn't it? FeOH thrice plus 3 HCl. So here the ionization part will be, completely ionization part will be the salt as well as the acid, isn't it? So FeCl3, it will be ionizing as Fe3 plus plus 3 Cl minus plus 3 H2O. Okay, so these two parts will be ionizing completely, giving FeOH thrice, it will be remaining as such, plus 3 H plus 3 Cl minus. Okay, so here the 3 Cl minus will be cancelling each other. So the resulting will be Fe3 plus plus 3 H2O, giving FeOH thrice plus 3 H plus. So here also the resulting solution will be having H plus ions in excess. Therefore, the resulting solution will be acidic due to the presence of H plus ions. Okay, the resulting solution will be acidic due to the presence of H plus ions. Hope you are clear with the first group of salt hydrolysis, that is hydrolysis of salt of strong acid and weak base. Then the next part, the second one, that is the hydrolysis of weak acid and strong base. Weak acid and strong base. Here also all the steps are the same. The only difference will be coming in the case of whether it is a weak acid or a strong acid, or a weak base or a strong base. There comes the difference. The steps are all the same. Okay, so again let us consider the hydrolysis of the salt Ba. So Ba plus H2O, giving BOH plus HA. BOH plus HA. So here this the hydrolysis takes place in the case of the salt, and also it is a strong base. So therefore these two parts gets completely dissociated or completely ionized. So we can write it as B plus plus A minus plus H2O, giving B plus plus OH minus plus HA. Again this B plus will be cancelling each other, isn't it? B plus will be cancelling, so the remaining will be A minus plus H2O, giving OH minus plus HA. Therefore we can write the equilibrium constant as K is equal to concentration of OH minus. This is the similar case that we are discussed in the first one, isn't it? There also we are finding out the hydrolysis constant KH. So here also K is equal to OH minus into concentration of HA divided by concentration of A minus into concentration of H2O. Then again this H2O we can take to multiply with this K. So it becomes K into H2O. So K into H2O, again it becomes KH, the hydrolysis constant, isn't it? K into H2O. So it will be KH KH is equal to K into H2. I am writing it here. So again we will be having OH minus into HA divided by A minus. Okay, so KH is equal to OH minus into HA divided by A minus. So this is equation number 1. So this is the hydrolysis constant of a salt of weak acid and a strong base. This is also important. All these formulas are important. You have to do the problems also with this formula. Okay. Then the next again, that is the relation between KH, Ka and Kw. So here we are taking a weak acid and a strong base. So therefore we are writing it as Ka. So again we had got this KH. Then we have to find out Ka and Kw, isn't it? So first of all Ka. So how will you write Ka? For Ka we have to write HA. HA will be ionizing as H plus and A minus. So Ka, the dissociation constant, Ka is equal to concentration of H plus into concentration of A minus divided by concentration of HA. Okay, so put it as equation number 2. Then we have to find out Kw. For Kw, we are writing the equilibrium of water. So water will be ionizing as H plus and OH minus. So Kw, that is equal to concentration of H plus into concentration of OH minus. Then again put it as equation number 3. Then again equation 3 divided by equation 2 as in the previous case. Equation 3 divided by equation 2, that is Kw by Ka, that is equal to Kw is H plus into OH minus, isn't it? H plus into OH minus divided by Ka means it will be H plus into A minus divided by HA. H plus into A minus divided by HA. That HA will be going to the numerator. So both H plus will be cancelled. So that will be equal to OH minus into HA divided by A minus. Okay. So what about this equation? Put it as equation number 4. So this equation number 4, it will be the same as the hydrolysis constant, isn't it? OH minus into HA divided by A minus. So therefore Kw by Ka, that is equal to Kh. So that is from equation 4 and 1. From equation 1 and 4. Okay. So again Kh is equal to Kw by Ka. Almost a similar equation. In the previous case it is Kh is equal to Kw by Kb. Okay. Then the next heading. I don't think there is any need for repeating all these derivations. You please go through once again if not clear. Okay. It's very simple. This derivation is very simple. Then the next one, that is the relation between